Okay, so hi everyone. This is our tutorial number 7. So actually there's a problem in the original tutorial recording that I had done, and the screen of this page in between the recording actually froze. So basically when I was solving through the pages and scribbling down the solution, so it did not show the full part of the solution in this recording. So many of the problems after this question number 1 were actually discontinued because I was actually solving them in the screen, but it is not showing in the recording itself. So that is why I am again re-recording this lecture tutorial. So in this tutorial I will not be again scribbling down the solutions to you, rather I will go through the problems and tell you the solution and its description in the um, as it is already solved in this alongside the problem. I'll just go through that, show you that, and tell you how it is done. And also I'll be sharing the this notebook's link this time, so you can get a direct access to the actually the page where the problems are solved and the solutions are written, so that it is more easier to you to actually get in sync with what I say with what I have solved. So extremely sorry for this inconvenience, but actually there's a glitch in the OBS recorder. I don't know how it has happened, but let us discuss and let us start all over again. So this is our tutorial number 7, right? So it is recording in OBS. It is continued. So this is again about superconductivity and the problems related to that. So I'll go through that. So the first question is about Josephson junction. So first let us read the question. Is that a thin layer of a superconductor is sandwiched between a thin layer of an insulator sandwiched between two superconductors constitutes a Josephson junction. The tunneling current density is given by J equal to J naught sine delta, where J naught is the maximum supercurrent density through the insulator with zero potential difference across it, and delta is the change of phase of the order parameter of the Cooper pairs across the junction. So then in the presence of AC voltage V across the insulator, the current density becomes which of the expression given in the options. So this is the question that has been asked to us, that we are being asked. So let us start again once again. So just once again, I will start the writing. Right. So I'll be using this color so that it is easier for you to highlight which of the parts I am talking about right now, or maybe a different color also, so that there are no confusions when I am redoing it. Okay, so let's say we use this color. Okay, so this is not properly seen. This color may be better. Yeah, so this is the color I'll be using to highlight the parts I am talking about right now, and you will just look into the solution that I have already done. So as it is about Josephson junction, and it is asked that what will happen to the critical current density that is tunneling through the junction, which is J in this case, when you apply a finite DC bias voltage V across the insulator regime of the junction. So you can see that the correct option is marked at option number 3 as this option, and how we got this is solved here. So basically this schematic over here is the schematic of a Josephson junction, where in between there is an insulating regime, which is this hashed regime, and on both sides of the insulating regime barrier there is a superconductor present. So on the left you have superconductor 1, and on the right you have superconductor 2. And this is the whole thing is actually consisting, the Josephson junction is actually consisting of this whole thing, two superconductors, and inside there is a insulating or non-superconducting regime. And we mark this left side superconductor as L and the right side as R, and a critical current not critical current density, but the supercurrent density that is actually happening by quantum tunneling of Cooper pairs is actually shown by this arrow mark here from the junction, and it is given by the term A, J. So J is the tunneling that is happening by the supercurrent through the Josephson junction. Okay, and here in this case you can see that this junction has been given a potential, which is in this case a DC potential, which is time independent. This V bias or V potential is given across the junction, and so we need to calculate what is the value of J when this V bias voltage is applied to the junction. So first of all, you know that when the first option was that when there was a zero potential difference across the junction. So that is the definition of DC Josephson effect. And what is that? Basically, first of all, in Josephson effect, you have the superconducting side. One superconducting side has a wave function of the electrons or Cooper pairs as psi l equal to root over of nl e to the power of I phi n, where root over nl is the density of the electron of the superconducting Cooper pairs on the left side of the superconductor. And similarly, if you define the wave function on the right side superconductor, it is psi r equal to root over nr e to the power of I phi r, where nr is the number density of the Cooper pairs on the right hand side superconductor. Phi l is the coherent phase associated with the wave function, which is a coherent wave function on the left side superconductor, and psi r is a similar coherent phase for the right side superconductor. So basically both of them are different and denoted by psi l and psi r, and these are actually this actually order parameter with the phase phi, and there is an amplitude part which is given by the square root of the Cooper pair density is a order parameter of the superconducting state, and this whole thing is from the idea of Ginzburg-Landau mean field theory, that you can define a wave function which has an amplitude part given by the number density of Cooper pairs known as the order parameter, which helps us to know whether you are in an ordered state. In this case, in a superconducting state is the order state, so your Ns will be non-zero. But as soon as you make a transition into normal state, that means it is not an order state anymore. So the Ns will be going to zero. Order parameter will be going to zero because there will be no Cooper pair left in the system. So this is the whole idea. Also, the width of the Josephson junction barrier, which is the insulating barrier in between the two superconductors, is of the order of the length scale zeta, where zeta is the coherence length of the superconductors. So coherence length means if you go outside the superconducting regime, so up to what length scale the superconducting property will still be retained, or what is the typical size up to which the Cooper pairs will still survive even if you go outside a superconductor. So that is the length scale of zeta. So very naturally, because inside the superconductor 1, when you are deep inside the superconductor 1, your this line is representing the the number density of the Cooper pair. So this is constant deep inside the superconductor, but as soon as you approach the junction between the superconductors, you approach the insulating regime, which is not superconducting anymore. So basically gradually your Cooper pair number density or the order parameter starts to fall down, and it actually decays over the whole coherent length scale, which is the junction width, that is zeta, which is given like this, right? Similar thing will happen also from the superconducting order parameter on the right hand side, that deep inside the superconductor 2, this has a constant value, and then as soon as you approach the junction in the insulating barrier, you actually see a decrease in the superconducting order parameter or the Cooper pair density value, and eventually we will see that it will decay down to a very lower value up to this whole length scale of zeta. So this is the idea of the superconducting order parameter on either side of the insulating barrier in a Josephson junction device. Now it is defined by the Josephson junction relation that delta is a phase difference between the order parameter on either side of the Josephson junction. So basically you have to take the coherent phase difference between the two superconductors alongside on both sides of the insulating junction. So basically in this case you have to take a difference between psi r and psi l. So your delta is psi r, sorry not psi, delta is phi r minus phi l, which is the phase difference between the two superconducting order parameters. Okay, phi r phi l, superconducting wave function's phase difference is given by delta. Now from the Josephson junction you will learn about two relations which are called Josephson relations. Okay, so the equation number 1 giving the relation 1 is basically that J equal to J naught sine delta. Okay, so when the bias voltage across the junction is 0, so your V equal to 0, no bias voltage is applied, then this relation is valid, that J equal to J naught sine delta, where J naught is the maximum supercurrent that can actually flow across the insulating barrier region via quantum tunneling. So you have to understand here that in Josephson junction there is actually a quantum tunneling that happens between the two superconductors, from one superconductor on one side to the other superconductor on the other side. A quantum tunneling of Cooper pairs will happen through the in between insulating regime. So normally you are familiar with a single electron quantum tunneling, but Josephson junction is an example where you see that quantum tunneling of a Cooper pair, which is two electrons paired up together, right? So anyway, so this is the relation that gives you the tunneling current across the VDF. So this is J equal to J naught sine delta, where J naught is the maximum current that can tunnel through, and delta is actually, this is a sinusoidal function of the phase difference delta between the superconducting wave function on either side of the junction. Okay, and this is time independent because this is there is no bias voltage given, so this whole current is not time dependent. That is what it is called DC Josephson effect, because it is not changing with time. But when there is a finite DC voltage is applied, which is V not equal to 0 is applied across the barrier, so finite DC voltage is applied across the barrier, which is this. So then a time dependence comes into the picture, because there is a second Josephson relation which will be valid or useful for this case, which is equation number 2 of Josephson devices, which is that del delta of del T equal to 2E V by H cut, or the time derivative of the phase difference between the two sides of superconductors of the junction is equal to 2E V by H cut. That means it is dependent on the bias voltage that you have applied across the junction, right? So that means now the phase is not time independent, but it has a time dependence. So if you just integrate it over here, you will see that this del delta del T equal to 2E V by H cut. So if you just integrate it, you will see that, sorry, so here this is given that if your del delta del T equal to 2E V by H cut from the second Josephson relation, then if you just take a derivative, take an integration, so it is just delta T equal to 2E V T by H cut plus some integration constant which is called delta naught, let's say. So this is the whole expression of delta, which has a time dependence now. This is the constant part which is time independent, which can be same as the DC Josephson effects phase sine delta. So this is same as this delta naught, because at V equal to 0, when there is no bias applied, delta T equal to simply delta naught, or we reduce it to DC Josephson effect, and you get J equal to J naught sine delta, where delta is your delta naught, which is time independent. Okay, that means it is a DC. This current does not change with time. But for AC Josephson effect, which is this case asked in the question, that you have a finite V not equal to 0 voltage applied. So the right hand side is not, this part is not 0. Instead, the net expression of the phase is now modified to a time dependence term like this. So then your critical, your tunneling current density J will be, so your J will be a time dependent term, time dependent current. So this is just J naught sine. So instead of delta, you put the whole expression here. So it is 2EV T by H cut plus delta naught. So this is the AC Josephson effect, because this current is AC, because this is varying over time. So this is AC Josephson effect, because it has a tunneling current which is time dependent. Okay, so this is what is happening in this case, and you can see from the earlier solution that I had done over here that I have done the same thing, that if delta is a phase difference phi r minus phi l, then for DC Josephson effect, your delta T is equal to time independent constant term delta naught, and simply J equal to J naught sine delta naught for V equal to 0. But when your V is not equal to 0, then you are reducing it to AC Josephson effect. Because why AC? Because your del delta del T part is non-zero now, so it has a finite value, and once you integrate, you get a time dependent term that is modifying the net phase difference delta. And if you just substitute the delta now in J equal to J naught sine delta, so you will get a term like this, where delta has a time dependence. So the entire current, tunneling current, has a time dependence. That is what you are calling it. That is why you are calling it an AC Josephson effect, because the current you are getting is alternating over time. So this option is option number 3, that is right. So already solved. Okay. Now question number 2 is again something that I have solved before. So it is, let us read the question first and then I'll show you the solution I had done before. Okay, so it is asked that the critical field for niobium is n into 10 to the power of 5 ampere per meter at 8 Kelvin and 2 into 10 to the power 5 ampere per meter at absolute 0. Then find the value of n if the transition temperature of the element is 11.3 Kelvin and given that n is an integer. So you have to give an approximate answer. So let us go to the solution I had done before. Also, so just to show you that I had inserted a Josephson equation or Josephson junction picture for a better understanding of the schematic for you. So this is the same schematic that I had drawn earlier, that this red part is your insulating regime. So it is an insulating regime in between the two superconductors. So this is the superconductor on left and this is the superconductor on right. And the wave functions of the superconductor on both sides are written by psi l e to the power of phi l and psi r e to the power of phi r. Okay, just as I had written before. And the Josephson tunneling current, that is the blue arrow, is passing across the junction from one side to the other side. And you can see how the wave function is decaying as it is approaching the junction and passing through the junction. Because initially you see that wf means wave function. It was a time dependent periodic wave function going like this one. Okay. But as soon as you reach and approach the junction, you see that this is decaying. This is going smaller and smaller, and now the frequency has been decreased. Okay. But because this width is zeta, because this is a zeta width of the tunneling barrier in between the two superconductors, so over this entire width, the superconducting wave function will not decay completely to 0, but it will survive up to this width. Okay. Similarly, from the other side, it was initially like this, the wave function, and then as soon as you approach the barrier, so it is actually decaying. Sorry. So yeah. So this is what is happening, and this is actually a schematic of the Cooper pair, because there are two electrons that is being tunneled by this Cooper pair tunneling in the Josephson current across the barrier. And these are the main two Josephson equations of superconductors. The first one is for the current. It can be also written as I, or if you want to write in current density, then you can use J. So this is I equal to IC sine. So instead of phi, we are denoting it by delta for lesser confusion, because delta is just phi r minus phi l. So they are meaning the same thing and denoting just by phi, but we will rather use delta. And they have used, instead of current density, they have used current. So, and the maximum critical current is represented not by J naught or I naught, but it is given by IC. So you can also write IC, or you can also write it as I naught, whatever you please. So this is sine delta, or in current density terms you can write J equal to JC sine delta. This JC you can also represent by J naught. Okay. And the second equation is the time derivative. So it is d. So instead of phi t, you can write it as delta for better understanding. So that there is no confusion with any other phase. So d delta dt equal to 2EV t by h, that as I had mentioned earlier. And these two equations we had used to actually solve the first question. So this can also be written as 2 pi v by phi naught, because if you just decompose it, so it is 2EV by h cut means it is h by 2 pi, right? So this is basically v by h by 2e into 2 pi. So I have taken the 2 pi on top and taken down the 2e below h. So you know that your h by 2 is nothing but the flux quantum. So it is just 2 pi v by phi naught, where phi naught is equal to h by 2e, which is the quantized magnetic flux. Okay. So this is done. Now for question number 2, we are solving that for niobium, which is a superconducting material, its Tc is 11.3 Kelvin, but the critical field value, which is Hc, because the unit is ampere per meter, so it is not magnetic flux density Pc, but it is the critical field Hc. So at t equal to 8 Kelvin, the critical field value is this, where n value is unknown and we have to solve. N is an integer. And for t equal to 0, Hc is given as 2 into 10 to the power 5 ampere per meter. So for this, we'll have to use this expression, that Hc t equal to Hc0 into 1 minus t by Tc whole square. So this is the expression for critical field for superconductors, and the graph is something like this, that if you plot in the y-axis Hct and the x-axis is t, Then at t equal to, this graph goes like this. So this whole graph is actually your graph. And at t equal to 0, that means at this point you see that the value of y-axis is hc0. So this is the t equal to 0 value for the critical field. So this is hc0, this is the maximum value of the critical field. Now as you go on and increase t, so along this line, along this arrow, if you follow, you will see that this is gradually decreasing. That means the critical field value is gradually decreasing as you are increasing the temperature. Just like that, if you take this point where this is at t equal to t1, you see that this marks at this y-axis where the value of the y-axis is lower than the earlier value at t equal to 0 Kelvin. That means this HCT1 is obviously lower than HC0, as it should be, because I told you from this equation that as you increase your temperature, you can see from this expression that your HCT will be even smaller than HC0. And finally, as it keeps on decreasing with temperature increase, finally there will come a point where your T is equal to Tc, or the critical temperature, that is this point, where the graph actually touches the x-axis. That means the y-axis value is 0 or HCT is 0. So at critical point temperature, the critical field value is 0, but at 0 Kelvin temperature, when it is the deepest inside the superconducting state, then the critical field value is the maximum, which is HC0, right? So simply by using, we can use the equation to actually show you that, I use the equation to show you that if you put t equal to Tc over that expression, then you will get that this is HC0 into 1 minus 1 whole square. It's just nothing but 0, as we also saw from the graph. But at t equal to 0, if you put t equal to 0, then the second term is just 0. So you just get HCT equal to HC0, which is the maximum value of the critical field. So that means at 0 Kelvin, your deepest inside the superconductor, and that is why your critical field value is maximum. That means the field that is needed to transform it from superconductor to normal metal will be the maximum of its value. That's why maximum HC is required to convert it into normal state. But at t equal to Tc, when it is already at the transition point, that means it is already at the verge of being a superconductor, from a superconductor to a normal state. So it's already in normal state by t equal to Tc. So field required to convert it to normal, or basically in other words, the critical field will be not needed at all. So that is why AC will be 0 at 0 Kelvin. Sorry, at t equal to Tc. So I hope these things are clear already. So you can directly use the expression, and you can take a ratio of HCT and HC0. So it will be just 1 minus T by Tc whole square. Then we will substitute the value of HCT, which is the 8 Kelvin value, which is given as n into 10 to the power 5, and HC0 is given as 2 into 10 to the power 5. So in the ratio, this 10 to the power 5 term cancels out. So you are only left with n by 2, this term. And on the right hand side, 1 minus T by Tc whole square. So instead of T, you place T equal to 8 Kelvin. So you put 8. And your Tc was 11.3 Kelvin for niobium given in the expression, so in the question. So you put 11.3 here. So it is just 1 minus 8 by 11.3 whole square. If you calculate, you will get that this is 0.498. And your n value is just 2 times that. So it is 0.997, which is nearly equal to 1. So basically, you see that you got the answer. N is nearly equal to 1. So your HC at T equal to 8 Kelvin is nothing but 1 into 10 to the power 5 ampere per meter. Now just to cross verify some of the things, I also showed you that this value 1 into 10 to the power 5 ampere per meter is actually smaller than the value of HC at T equal to 0 Kelvin, which is 2 into 10 to the power 5 ampere per meter. So your HC at T equal to 8 Kelvin is lower than HC at T equal to 0 Kelvin, and this is evident because we already justified the fact that at 0 Kelvin the critical field value will be maximum, because it is the most deepest inside the superconducting regime. So it will not be easy to actually convert it into a normal regime by a small critical field, and that is why the HC is maximum or greater than any value at a finite temperature. So 8 Kelvin is a finite temperature which is below the critical point temperature 11.3 Kelvin. That means the IBM is still in superconducting state, but because it is actually not 0 Kelvin, so the critical field required to make a transition into normal metal is actually lower than the critical field at 0 Kelvin. So this is cross verified. So our problem is solved accurate. Now let us move on to our question number 3, which says so basically we got the answer as 0.997 and or nearly equal to 1, and you can see the probable answer range is given between 0.9 to 1.1, so you are inside within that range, so our answer is correct. Then question number 3 is that to measure very tiny magnetic fields, which one of the following instrument is most useful? So the note undoubtedly the most useful instrument will be squid, which is the first option here. So squid is the answer. Now squid is basically a device which is formed by two Josephson junctions, like this one, this picture. That this is a schematic of the squid where this part is one Josephson junction and this part is other Josephson junction. So in other words, you can draw it like this is a loop like thing. So like this, okay. So and here there is one Josephson junction, so this is the insulating barrier in between, and in bottom there is another Josephson junction, so another insulating barrier in between. Otherwise, other than that, these parts, all these parts are just superconducting materials. Okay, so these dotted parts I am drawing, these are made of superconductors. Okay, and this dashed part are the insulating regime. So and this part that is inside this loop, this is basically a normal regime, so the magnetic flux can penetrate inside and will be trapped inside, and this flux is denoted by phi. So a current will be incoming to the device, which is I, and face each of the Josephson junction. This is Josephson junction 1 and this is Josephson junction 2. So the current will be flowing through or passing through, tunneling through each of the Josephson junctions. So this is I1 tunneling through Josephson junction 1 and this is I2 through tunneling through Josephson junction 2. And finally the current that will be output is IT, I total. IT is nothing but I1 plus I2. Now you know from Josephson junction, for a single Josephson junction, you know the tunneling current is given by I equal to IC sine delta, right? So for if Josephson junction 1, this parameters are IC1, the critical current for JJ1 is IC1 and the phase difference for this case is delta 1. Similarly, for Josephson junction 2, the critical current value is IC2, let's say, and the phase difference is delta 2. So simply this I1 plus I2 will be IC1 sine delta 1 plus IC2 sine delta 2, as I had already solved before. So basically this is a schematic of the whole squid structure, that this is the main diagram and this is the schematic, right? Both are similar. So this is the squid schematic and squid is consisting of two Josephson junctions, okay. Now this system can actually capture very tiny magnetic field as small as 10 to the power of minus 14 Tesla. It is a quite tiny magnetic field that squid can detect very sensitively. And in magnetization units, you can also write it can detect up to 10 to the power of minus 8 EMU. So this is the lowest value of magnetization that squid can measure or detect. And the noise level is so small that the noise level is almost 3 femtotesla per root over hertz. So basically it means that 10 femtotesla is 10 to the power of minus 15 Tesla. That means the noise level for the magnetic field detection is 10 to the power minus 15 Tesla for the squid. That means you can safely and accurately detect the magnetic field without any noise up to 10 to the power of minus 14 Tesla. This cannot be done by any other magnetometer, because that the noise level will be so high that it cannot sensitively detect such tiny magnetic field components in the background of the noise. So that is why squid is the most efficient to measure very tiny magnetic fields. So question number 3, option number 1. Now fourth question is that, again a mathematical question, is that in an experiment an niobium wire of radius 0.25 millimeter is immersed in a liquid helium bath which has a temperature of 4.2 Kelvin and it carries a current of 300 ampere. Then what is the magnetic field that is inside the current carrying wire? That is actually generated by the current. Okay, so your given critical temperature of niobium here is 9.3 Kelvin. Now as I had written over here that the typical TC of niobium, which is mentioned in the question also, is 9.3 3 Kelvin, and the liquid helium bath in which the niobium wire has been immersed is sitting at equal to 4.2 Kelvin. That means it is lower than the Tc of the niobium, 9.3 Kelvin. So since the T is lower than Tc, we can say that the niobium is in superconducting state, that is T is less than Tc when it is immersed in the liquid helium bath. So we are dealing with a superconductor which is below its Tc. Now let us go to the bottom part where I have solved this question. So this is the question, that if you have a current carrying wire like this, I current is flowing through, so you will have a magnetic field that will be generated by the current around this wire, which is this loop over here, which is a particular direction, in this case anti-clockwise, because the current is in the upward direction, and this is the magnetic field that is generated by the current in the wire. Now this is a well established expression from electromagnetism, that for any current carrying wire, the magnetic field that will be generated from it will be given by this expression, B equal to mu naught I by 2 pi r, where I is the current, mu naught is the free space permeability, and r is the distance from the axis of the wire. So let's say if you think of it like a cylindrical shape of the wire. So this is a cylindrical wire, and the radius of the wire is A. Okay, so the radius and the entire radius of the wire is A, and this is the axis of the wire, cylindrical wire, which is the current I is actually following along the axis. That is why we have put I over here along the axis. And let's say this r distance is some distance, arbitrary distance from the axis of the wire to up to this point. Okay, so this is the r distance. So if you have to calculate what is the magnetic field that will be at this point, r distance from the axis, so it will be given by this expression, mu naught I by 2 pi r. Now for our case, the only length information that we know is the radius of the wire. So instead of taking r as any arbitrary value inside the wire, we will be using r to be equal to the radius of the wire, which is A. And it is given in the question that it is 0.25 millimeter or 0.25 into 10 to the power of minus 3 meter. And the current in the wire is 300 ampere, so I is 300 ampere. Then the flux that is generated, that the magnetic flux density, this is not flux but this is flux density, or B, that is generated within the niobium wire, is given by this mu naught I by 2 pi. So we just directly put the expression of each of the terms. So it is mu naught is 4 pi into 10 to the power minus 7 in SI units. Then the current is 300 ampere, and 2 pi into the radius is 0.25 into 10 to the power minus 3 meter. So you get a value of B as 0.24 Tesla, which is our answer, that this is the field that will be generated by the wire inside the wire because of the current flow. Now just to cross verify some of the things, I have also shown you here that since you are sitting at the niobium wire is sitting at 4.2 Kelvin, so what will be the critical field value for the niobium wire at 4.2 Kelvin? So we have calculated Hc at 4.2 Kelvin by the same formula that we had used in question number 2. So this is Hc 0 into 1 minus T by Tc whole square. So this is basically your T by Tc whole square. And from question number 2, you can directly use the rough approximate value of Hc0 from question number 2, because the material is the same niobium for both question number 2 and 4. So we have taken the value of this critical magnetic field value at 0 temperature from question number 2. This is 2 into 10 to the power 5 ampere per meter. Then instead of T, we have placed 4.2 Kelvin, which is the liquid helium temperature where the niobium is immersed inside. And Tc is given as 9.3 Kelvin, and by solving this we can get Bc at equal to 4.2 Kelvin just by multiplying this Hct by mu naught, because you know that B equal to mu naught H, right? So similarly Bc at 4.2 Kelvin will be equal to mu naught into Hc at 4.2 Kelvin, which is what we had done here, that if you solve the Hct from here and then multiply it by mu naught, you will get a Bc value at 4.2 Kelvin as 0.198 Tesla. Now you can see that this critical field value at 4.2 Kelvin is lower than the field that is generated by the magnetic field that is generated by the wire that is sent through the niobium wire, right? So this is 0.198, which is the critical field of the the critical field of the niobium, and in this case, and the field that is generated by the current that is being carried by the wire is 0.24 Tesla, which is greater than the critical field value of 4.2 Kelvin. So in this case, I have made a mistake probably because this line is not right, because you can see that the field that is generated by the current that is carried by the superconducting niobium wire is actually exceeding the critical field value for the temperature. It is greater than that value. That means we have already, by the critical field application, even if we are below TC, we have already transformed the niobium from a superconductor to a normal metal, because this field is greater than the critical field, and so it will break the Cooper pairs inside the superconductor, and as a result, it will be turned into a normal metal. So, because the current generated magnetic field B exceeds the critical field BC at that temperature equal to 4.2 Kelvin. So the magnetic field will help to break the Cooper pairs. So Cooper pairs will be broken, and the superconducting niobium will be turned into normal. Will turn into normal. That means it has no superconducting property. As a result, the magnetic field lines or flux lines, which are earlier would not be able to penetrate through the superconductor, but now since it has turned into a normal state, so the field or the flux lines can be penetrating right through it. So this can be penetrated inside the superconductor. So inside the superconducting wire also, the flux value will be same as outside. So now B is not equal to 0 inside it, because it is not superconductor anymore, and the value of B that we have calculated inside the wire is 0.24 Tesla, that is caused by the 300 ampere current flow inside the wire. Okay, so we got our answer. So the answer is 0.24. Okay, so correct up to 2 decimal places is asked in the question, and the correct range is between 0.2 to 0.3. So our answer is reasonable in the regime. So this is the correct answer that we have solved for this question. Then question number 5 is about determine the temperature at which the critical field becomes half of its value at 0 Kelvin if the critical temperature is TC. So again the same formula you have to use, the critical field formula. So question number 5 is about HCT equal to half of HC0. It is given in the question that HCT equal to half of HC0. So if you take a ratio, HCT by HC0 will be half. Then you equate the ratio to 1 minus T by Tc whole square, because that is from the formula well known. So 1 minus T by Tc whole square will also be equal to half. So you can solve it further and get T by Tc whole square equal to 1 minus half, which is half. So your T by Tc equal to 1 by square root of 2, or in other words your T equal to Tc by root over of 2. So this is the answer that will be in this question. So let us choose the answer. Yeah, so the first one is the correct answer, that T equal to Tc by root over of 2. Then question number 6 is that a superconducting ring carries a steady current in the presence of a magnetic field normal to the plane of the ring. Then identify the false statement. Okay, so out of the 4 options, one statement is false and you have to identify that. Option number 1 is that the flux passing through the superconductor is quantized in units of Hc by E. So this is obviously the false option, because for a superconducting ring, you know that the flux quantum is given by not Hc by E but Hc by 2E, because in superconductor the main carriers are the Cooper pairs, which has 2 electronic charge. So its charge is 2E instead of E. So that is why the flux quantum is not Hc by E but it is Hc by 2E. So this is the flux quantum value, that it is Hc by 2E, and because it is in CGS unit, so there is a C term present, which is the light speed, light velocity. But if it is written in SI, then it will be just H by 2E. Okay. As for the other options, if we just look at and read how they are true, So you will eventually have to use the concepts about superconductors and superconducting rings. So the option number 2 is that the current and the magnetic field in the superconductor are time independent. So this is also true because if this is your superconducting ring, this is this dash blue regimes that I am again marking it over, and inside it is some other non-superconducting normal space. Because this is a ring, so inside it will be a normal space, and let's say there is a external there is a current that is flowing through the superconducting ring. That current is I, and because the superconductor has no resistance, its resistivity almost goes to zero by the superconducting property. So the current mode will be a persistent current mode, meaning that this I current that is once sent inside the superconducting ring or loop will for infinite time keep on flowing inside this loop without any dissipation. Because for superconductor the resistivity tending to zero, so there is no dissipation or dissipative nature present in the system. So because of that, there is no dissipation, so the current will not decay off over time and it will continue flowing in a persistent mode, and it will be time independent. Similarly, this current will generate a magnetic field. This is B that the current is generating, and that current and the magnetic field is also not changing over time. It is also time independent because these flux lines that are penetrating inside the superconducting loop are constant because the current is constant that is generating it. So, and do not get confused because for superconductor the magnetic field or magnetic flux density is zero. So inside the superconducting ring itself it is zero, but in the middle space of the ring where there is no superconducting material, there a flux will be trapped and there will be a time independent magnetic field. So this is true. And option number 3 is that the superconducting current density Js and B are related by the expression, and this is true because this is the generic London's equation of superconductors in series unit. So that is why curl of J equal to minus ns E squared by m into B vector, and if you put a CGS unit, so this will be a MC. Okay, this is also right. And the fourth is that the supercurrent does not decay over a very long time. This I have already discussed for option number 2, that because the resistivity or the resistance tends to zero for this case, so it is a supercurrent will flow without any dissipation and it will not decay over even a very long time. Okay, so except for option number 1, all the 3 options are correct. Now question number 7 is about again BCS theory of superconductivity and related to London's equation. So you have to choose the correct combination of equations, and the correct combination is equation number 2 because I had already solved it for you earlier. Just let us follow that. So your curl of J equal to minus ns E squared by mc B vector. This is already proved to be true from the earlier questions. Now you can represent your B as curl of A. So your curl of J equal to minus ns E squared by mc. Then the B you replace by curl of A, right? So if that is the case, one second. So B is replaced by curl of A. So if you express that here, so curl of J becomes minus ns E squared by mc curl of A. So you can get rid of curl from both of the sides and just write down J equal to minus ns E squared by mc A vector. This is the supercurrent density given and related to the vector potential A vector. So this is the first option is correct. First expression is correct, and this is the London's equation, another expression. Then again you can write down and find out what is the value of directly J from here. So both of these equations are verified that curl of J is the London's equation given by this term, and from there if you further derive you will get a J value like this. And if you further proceed, then you know that the curl of B equal to mu naught J, this is known from electromagnetic formula, and if you just take another curl on both the sides, then curl of J equal to mu naught, curl of B equal to on the other side mu naught curl of J, because mu naught is a constant, so it comes outside the curl. Then you can solve it. Curl of J equal to gradient of divergence of B on the left side, so this is known from vector calculus expressions, minus Laplacian of B. And you know, for superconducting case and for electromagnetism, the B is chosen such a way, the gauge choice is such a way that divergence of B is 0. So then you are only left with minus Laplacian of B, and on the right hand side, if you just plug in the value of curl of J from earlier, you get that it is minus ns E squared by mc B. So this minus sign and this minus signs actually cancel out each other, and you are left with curl of Laplacian of B vector equal to mu naught ns e squared by mc B vector. You can define this whole term as 1 by lambda squared, where lambda is a characteristic length scale known as the London penetration depth, and therefore you get an expression like Laplacian of B equal to lambda to the power of minus 2 B vector, and London penetration depth lambda is equal to root over of m into c divided by mu naught ns e squared, or in SI lambda equal to lambda L, London penetration depth equal to root over m by mu naught ns e squared. So your correct answer is option number 2, because the last option even matched, that type Laplacian of B equal to 1 by lambda square B vector. Okay, so this is right, except the answer is also matched as 2. Then option number 8, question number 8 is that which of the following Josephson effects is used to generate and detect electromagnetic waves of frequencies ranging from radio wave to infrared wave. So you know that there are two kinds of Josephson effects. One is DC Josephson effect and the other is AC Josephson effect. So in DC Josephson effect, you know that there is no bias potential or voltage that is applied across the junction barrier, which is for V equal to 0. And as a result, you get a tunneling current J, which is not again time dependent, but it is actually invariant over time. So you get a tunneling current J equal to J naught sin delta, and delta is the phase difference between the two sides. So this is the DC Josephson effect, but here there is no sign of some alternating current or alternating currents frequency. So rather, when you take the case of the Josephson junction being applied to by a bias voltage of V not equal to 0, then your phase part is getting modified to include a time dependent term, which is delta t equal to delta naught plus 2ev by 2ev t by h. So this is the time dependent term. Time dependent part of delta t, that is the modified phase difference value, and delta naught is the same, the constant phase that is actually used in DC Josephson bias effect. Okay, and your new AC Josephson effect tunneling current will be J equal to J naught sin delta t, where it will be equal to J equal to J naught sin delta naught plus 2ev t by h. So the only way you get the response in frequencies of radio wave to infrared wave is when you get an AC Josephson effect. That is why the answer will be AC. So option number 2. Then question number 9 is about the interior of a bulk superconductor cannot be penetrated by a weak magnetic field. In this phenomenon is known as, no doubt, Meissner effect, because Meissner effect is the effect that tells you for the first time that superconductors are perfect diamagnet. No magnetic field can either penetrate or enter inside the superconductor. Okay. And why it is called to be a weak magnetic field and not strong? Because there is a critical magnetic field value of the superconductor. If you exceed that value, then the material will not be superconducting anymore. So we have to be below the critical field regime, and that is a weak magnetic field that is being actually applied, and it cannot penetrate, even that cannot penetrate the bulk superconductor, because it has perfect diamagnetic property with B equal to 0 inside. Okay, so this is a schematic diagram, that if this is a superconductor inside B equal to 0, and there is an external field that is applied from outside on the superconductor. So these are the field lines. So far away from the superconductor, the field lines are just the same and parallel as before. But as you approach the superconductor, you will feel a repulsion of the magnetic fields by the superconductor, and that is why you get a distortion like this, repelled out or pushed out field lines like this. And this is for T is less than Tc, and the critical field value is actually low. Actually, the applied weak magnetic field value is actually lower than the critical field. So that is why it is still in superconducting state. So this is also demonstrated from here, this diagram and this image, that this lower bottom part is a superconductor which is in a liquid helium or liquid nitrogen bath because of this vapor like kind of thing here. So this is in a superconducting state, but this upper part is a tiny magnet that is applying a very weak magnetic field to the superconductor in this case, and because the magnet's magnetic field is not exceeding the critical field value, So it is still in the superconducting state, and still it will continue to repel the field lines from it away. So that is why you see that instead of the magnet falling down and touching the superconducting surface, instead it is as if suspended in the thin air on top of the superconductor. So this is the Meissner effect, and this happens because of the perfect diametric property. And this is the schematic of what happens to the field lines when the Meissner effect happens. Is that if you have a superconductor, which is this case is this one, and inside the superconductor you know that the field lines will be repelled, so B equal to 0. But outside you get to see the field lines are everywhere present, and it is as if getting pushed off by the material presence of superconducting material. Okay, so this is the idea, and the Meissner effect is valid option for this question. Then question number 10, or the last question, is about the derivation of London penetration depth. So it is asked that the London penetration depth of the elemental type 2 superconductor niobium is L into 10 to the power of minus 6 meter at T equal to 0 Kelvin. Then the number density of the superconducting electron is 1.8 into 10 to the power 24 per meter cube. Then what is the value of L? Okay, so in the hint it is already given the expression of lambda L on the London penetration depth, which is equal to root over of m by mu naught n e square. So this is in SI unit, not anymore in CGs. That is why there is no light speed c is present. So SI units, lambda L is equal to root over m by mu naught n e square. So m is the electronic mass, n is the number density of the superconducting electrons, and mu naught is the permeability of the free space. So you just directly use that expression and put the values here. So your m is 9.1 into 10 to the power minus 31, mu naught is 4.10 to the power minus 7, n, that is superconducting electron density, is given by 1.8 into 10 to the power 24 per meter cube, and E squared is 1.6 into 10 to the power minus 19 whole squared. So you get a value of 3.96 10 to the power minus 6 meter, or 3.96 micron. Or you can also round it off to look like 4 micron. So anyway, our answer is exactly 3.96 micron, and it is in between the regime of range of answers that is given between 3.4 to 3.5 to 4.5. So we are in between that regime. That means our answer and the solutions are correct. Okay, so with this, this week's tutorial is over. As I said that if you find it difficult to actually see the problem solutions because the recording is not in a sync mode with the note that I have put the solutions already inside, but for that you can just follow the recording, and you can listen to the recording, and you can actually look through the solutions that have been already done to match up the actual solutions. Okay, and I'll also be sharing with you, as promised, I'll also be sharing with you this OneNote pages link, so that you can also access it from there and look at the solutions that I have done. Okay, so okay, then meet you in the next tutorial.